Welcome. What we are going to see next is the estimation of the fugacity coefficient from the pressure, specific volume, temperature data at equilibrium. Note that we have already seen a method of estimating the fugacity coefficient at the end of a previous module, and this is going to be another method from the PVT data at equilibrium. So, we are going to use the condition of equilibrium to devise a method to estimate the fugacity coefficient. For a pure component, we have already seen this equation in module 3, d mu equals V dP under certain conditions. This was 353, and d mu equals R T d ln f. This was equation 354, f being fugacity. So, since these are equal, if we equate these two, we would get R T d ln f equals V dP. Let us call this equation 531. If we integrate this expression between saturated value and a particular pressure, let us say P1, we would get, this is dRT d ln f. We are going to integrate between a saturated pressure and a certain P1. Therefore, we will have to integrate the right hand side also. First, let us see the left hand side, d ln f, therefore, ln of f by f sat, ln f minus ln f sat, which is going to be ln of f by f sat, that equals 1 by R T integral from P sat to P1 V dP. Let us call this equation 532. If you recall, this is the molar liquid volume. The molar liquid volume is typically a weak function of pressure. At the temperatures well below the critical point, we really do not have to worry about its variation with pressure. Therefore, for all practical purposes of interest, this V can be taken to be a constant in this particular integral. It is a very good approximation. And what we are going to do now is to avoid the difficulty between, or the confusion between, the vapor and the liquid phase volumes. We are going to use another subscript L to represent, or to make it clear that it is the molar liquid volume, and so therefore, we are going to call it as VL. This is actually a superscript L, and we are going to call it as VL. Therefore, we will get ln of f by f sat equals, this is 1 by R T, V also is a common, or VL is a constant that has come out. Therefore, VL by R T, and integral of P sat to P1 dP is nothing but P, or P1 minus P sat. We are just going to drop this 1 here. Therefore, P minus P sat, or f by f sat equals exponential of VL into P minus P sat by R T. Earlier there was a log here, therefore, f by f sat becomes exponential of the right hand side. Let us call this equation 533, and while we are doing all this, our main aim is to get at an estimate of the fugacity coefficient. Let us see how to go about doing that. This right hand side of this expression is actually called as the pointing factor. F by f sat equals this exponential of VL P minus P sat by RT. This is the pointing factor. Further, using equation 528, become clear right now, phi sat P sat was f sat, and this is again pure substance. So, phi sat P sat equals f sat is valid here. This was 528. We can write 533 as f equals phi sat P sat exponential VL P minus P sat by RT. Now, f sat f by f sat was exponential V L p minus p sat by R t. Therefore, f equals f sat exponential V L p minus p sat by R t. We have just replaced f sat by phi sat p sat. Let us call this equation 534. Now, phi is nothing but the fugacity coefficient is nothing but f by p. Therefore, the above equation can be used to find the fugacity coefficient of a pure component that we have somehow arrived at in, but let us clarify that a little further. That was for a pure system. We need that for now. We need to look at a multi component system. That is what I meant by clarifying further. We need to do it for a multi component system. For a multi component system, this equation 530 is valid, which is phi I p y I equals gamma I f I x I. This is what we derived, in fact you had derived for a multi component system, the condition for equilibrium being this phi I p y I equals gamma I f I x I, equation 530. Note that the f, which is fugacity of a pure component, equals f I, which is the fugacity of the pure component I at the same temperature and pressure as that of the solution, that is the fugacity when phi y I equals 1, when the mole fraction equals 1. Therefore, using equation 534 to substitute for f I in 530, we get phi I p y I, that is the left hand side, equals gamma I, same as gamma I here, x I same as x I here. Instead of f I, we are going to write phi I sat p I sat exponential of V I L into p minus p I sat divided by R t. We just substituted f I with the one that includes the Poynting factor here, which can further be written as phi I into p y I, which is the left hand side, equals gamma I p I sat x I. Now, this, if you are able to see this, I have let me show you what phi I is, then it will become easier. This is what we have here. We have written this expression as, this is a okay, let us call this phi. Okay, this is not phi, let us call this phi. Phi I into p y I equals gamma I p I sat x I, which means the remaining terms have all been combined into a phi I, which is what will be shown here, where phi I equals phi I divided by phi I sat exponential of minus V I L p minus p I sat by R t. Let us call this equation 536. And what usually happens is that the exponential term is close to unity at pressures of relevance to most biological systems, which is typically atmospheric pressures and so on and so forth. Therefore, this term can just be replaced with a 1 for most biological systems, and the following approximation works very well, which is phi I equals phi I by phi I sat, equation 537. The value of phi I can be estimated from the second virial coefficients. Remember that b 1 1, b 1 2 2 and so on and so forth. We can use that to estimate phi I. I am just going to state it here, I am not going to derive it in here. The derivation requires probably some understanding of statistical mechanics. Phi I equals this complicated expression, let me just read it out to you, equals exponential of b I I p minus p I sat plus half and twice summed over j and k, yj yk 2 delta j I minus delta j k. I will tell you what deltas are, delta 2 delta j I minus delta j k divided by R t. This is equation 538, where delta I k equals 2 b I k minus b I I minus b k k, and delta I j equals 2 b I j minus b I I minus b j j, and delta I I equals 0, delta k k equals 0, and delta k I equals delta I k. Therefore, there is a way of estimating this phi I from the second virial coefficients, and going back you can get the other quantity that we are looking for. And what we did in this particular section is to look at a way or a method of estimating the fugacity coefficient from the conditions of vapor liquid equilibrium. Since the other things are slightly different, let us start them in the next class. We will stop here for this class. See you in the next class.